Thank you very much, Iju, for the kind introduction. And again, I'm really, really sorry for not being able to be there with you today. I hope that you are going to be able to see my screen in just a little bit. Okay, hopefully everything is fine. So, hello, and I really wish that I could be in person today to deliver this talk and discuss with you. But unfortunately, as Iju has said, I cannot. So I really hope to have an interaction with you at the end of this talk. I plan to talk about how the study and incorporation of time as an impactful and non-trivial factor represents an exciting and extremely impactful frontier in machine learning. But before I talk about time, I want to take a short detour and say a few words about the current state of artificial intelligence and machine learning. In the past few years, we have seen significant advances in AI and machine learning, including in natural language processing with ChatGPT, computer vision, robotics, and many other fields. And yet, one needs to wonder, has AI transformed healthcare systems? For instance, has AI fixed issues with the NHS in the UK or enabled us to control the exorbitant costs of US healthcare? Can we alleviate traffic control? For many years, I was stuck in traffic while I was working in Los Angeles. And can we solve the energy crisis or prevent a climate catastrophe? And do we have machine learning that can help us avoid the next financial crisis? As an educator, as a researcher, but especially as an educator, I envision really a Roman schoolmaster walking in 2023 in a classroom. And my guess is that he or she will recognize immediately what is going on in the classroom of today. Not much has changed in 2000 years. I also believe that we are not just a few breakthroughs away in solving these real-world challenges. And note that I'm not saying that machine learning cannot solve these challenges or cannot play an important role in these real-world problems. Rather, what I'm trying to say is that we need to think fundamentally differently about machine learning and orient it towards solving the complexities of the real world. And
Recording in progress.
And to do this, I strongly believe that a fundamentally new paradigm is needed for AI. This is why I have developed the Realitycentric AI agenda to reorient AI towards the complexities of the real world. You can read the manifesto paper that I have written together with my collaborator, Andrew Rashbas, on this website. And you can see there a research agenda that we put forward for the community to discuss it. I'm going to say just a few words about it here. And what I mean by reality-centric AI is AI which aims to solve real-world problems, which operates effectively and accountably given inherent and unavoidable complexities of the real world, both real data, agents interacting with each other, environments changing. So what I'm trying to advocate here is moving away from toy problems, which we often solve in the machine learning community, and focusing on these complex real-world problems with a goal of empowering rather than marginalizing humans. I also like to say that solving such real-world challenges is important, but very hard. I've spent an entire career working on such complex systems. I worked on smart cities, transportation, finance, energy grids, education, economics. Somebody can say that I have a little bit of an attention deficit disorder, but the reality is that I was fascinated by various problems of the real world, and I tried to do whatever I could to solve them. Most recently, I'm working on medicine and healthcare, and I'm developing AI tools to empower these domains. And I really believe that even though very hard, solving such complex human-centric problems is our biggest task as machine learning researchers and data mining researchers. And today I want to tell you in this context about the concept of time and why I believe it's such an important problem that should really be our next frontier in order to solve many problems in the real world. I'm going to talk today about 4 interrelated problems which involve time: early warning, early diagnosis, causality over time, and discovery and understanding of complex dynamical systems. And to illustrate why these problems are impactful and exciting, yet challenging, I'm going to outline some, not all, the challenges that these problems pose. And I'm going to tell you a little bit about what we have done in this area, not because we are the only ones to have addressed these problems, but just to show you how we have struggled with these problems and how we engage with the real-world problems they pose. I call these canonical problems because they are fundamental problems and they transcend the application domain. They are important in healthcare, in energy, in finance, in transportation, in smart cities, in environmental science, and many others. And I do believe that time requires new ways of thinking for machine learners. And I really hope that I can convince you today that this is an exciting agenda, and hopefully you will join me in this agenda. And I'm not saying that these problems have not been addressed in other fields, for instance, economics, engineering, and others, but they have mostly been addressed without the power of machine learning. So what I'd like to do today is to convince you all that the machine learning and data mining communities need to join forces with other communities to engage and solve these real-world problems. Let us start to talk about the first problem, early warning systems, where our goal is foreseeing potential issues of risk in a system, like, for instance, an impending disaster like COVID, financial crisis, or the need for a patient to be admitted to the ICU. So early warning is a proactive aim, which focuses on predicting problems before they occur. And by utilizing monitoring and historical data, the system learns to timely predict various adverse events of interest. I'm going to start by giving you an example from healthcare. Unfortunately, in healthcare, we do not have a lot of data available that's time series data on which we can do machine learning. But fortunately, we have the MIMIC dataset, which contains multiple measurements and streams of measurements that are acquired about patients that are hospitalized and are monitored frequently. These measurements are sparse, irregular, and informatively sampled. Let me just say a few words about informative sampling, because I'm going to return to this later as well. These measurements of patients are not measured at random. Clinicians and nurses are taking measurements about a patient when this patient is especially not feeling well. So what I mean is that the moments in which this information is present or not, it's informative about the underlying state of the system, in this case, the patient. Also, we have many possible patterns. Different patients stay for different lengths in time in the hospital and deteriorate or improve differently. And on the basis of this, what we want to do is early warning systems for various events of interest. For instance, is the patient going to need admission to the ICU? Or is the patient needing to get ventilator or antibiotics? At this stage, you may wonder, well, but this is actually a very solved problem because we have numerous dynamic and recurrent models. Here are just a few. Among them, transformers, which we all know has been an important workhorse for the current success of large language models. So can such dynamic and recurrent models solve this early warning problem? And the answer is no, because this is not a classification or a regression problem. Unlike in time series forecasting, where we have continuous monitoring and prediction, where we try, for instance, to predict either the next biomarker or the next signal, or we are trying to predict whether this patient is going to die in the hospital or be discharged. In early warning systems, in time to event analysis, we are focusing on understanding the underlying time distribution until that event of interest occurs. So the primary focus in early warning is on estimating the time until an event of interest occurs. We are not interested in forecasting the next, again, biomarker, but rather getting a timely warning that the patient, for instance, will need admission to the ICU. And we want to know, for instance, how long will it be until the patient will need this admission. While I give an example from medicine, I'd like you to keep in mind that early warning systems are useful in many other application domains. And I'm giving you here just a few examples from my own past research. For instance, in finance, we have time-to-event analysis that can be used to model the time until a borrower defaults on a loan. Or for customer churn prediction, we analyze the time until a customer leaves a service. In smart cities, the focus is often on infrastructure failure prediction, and time-to-event analysis, early warnings can be applied to predict the failure time of critical infrastructure, for instance, bridges, roads, or water supplies. In emergency response time modeling, we are interested in understanding and predicting the time it takes for emergency services, for instance, the fire department, to respond to a call, and many others. Why do we care about early warning? Because it enables us to do better planning, maintenance scheduling, risk mitigation, and resource optimization. Let us look at this in a little bit more detail. I'm going to first talk briefly about the static setting. What you see here is time-to-event analysis, which in statistics often is called also survival analysis. And what you see is a patient with different ages and the probability of death of this particular patient due to an event of interest. What you see here is a specific scenario, a specific setting that I'm working on, which is cystic fibrosis, where unfortunately patients are affected by the disease young. So what you see is that patients may die, for instance, due to respiratory failure or due to other competing events. But what we are interested in is not to do that statically, but to change our time-to-event analysis as we acquire more data. So what we need is to compute sequentially this time-to-event analysis as more data becomes available. What you see here is a green and a red curve that's changing over time. And these are just two biomarkers that are measured regularly about cystic fibrosis patients. And they are indicative of the probability of events of interest. And you see how this is changing every time a new information becomes available. So I'd like to highlight here that an important challenge is that we would like to do this time-to-event analysis not one event at a time, but rather jointly. So we would like to deal with multiple competing risks. Let me now say a few words about this data. And I'd like to talk about this data that we use for time-to-event analysis because it has both similarities but also differences with conventional time series data classification and regression. On one hand, we have history of longitudinal measurements until the last measurement, and on the basis of this, we want to do this time-to-event analysis. The data contains two more things. One is the event of interest, and most of the time, as I mentioned, there may be multiple types of events. You see here, for instance, different patients with different types of events. But again, keep in mind that this is not just for medicine. And also, I'd like to draw your attention to the third patient, where what you see is that the patient is rightly censored. What do I mean by that? This is a situation where the patient left this study, this data set, and we do not know what it has happened to them. So this is known as right censoring. And what's important is to realize that such censored patients or such censored data are also informative, and we shouldn't discard them, but rather learn from them. So again, two differences to the conventional time series prediction problem. We have multiple events of interest, We are interested in the time at which these events are happening, and we have brightly censored data that we need to learn from. So what is the objective in this case? How do we build these early warning systems? We are going to use cumulative incidence functions. And what we have done in this work a few years back is to take these cumulative incidence functions and extend them for the dynamic time series setting. Prior to this, we couldn't find anything in the literature that dealt with this dynamic incidence function. So these cumulative incidence functions allow us to estimate the incidence of the occurrence of an event while taking competing risk into account. And we are doing that on the basis of longitudinal measurements recorded until the last observation. So what you see here highlighted in green are the longitudinal measurements accrued by the time of the current risk prediction. And what you see highlighted in blue is the event of interest that did not take place until the time of the last measurement. And what we are trying to predict is a probability that is changing over time of the event K. And again, we have multiple events happening at this particular moment in time, capital tau. So how do we really model this? Well, because we have multiple competing events, we decided to have a multitask architecture. And this is common in other settings, even in prediction in machine learning, where we have a shared subnetwork, which is an RNN with attention. And we have multiple cause-specific subnetworks dedicated to the prediction of every event of interest. But the architecture is not the interesting part here. As a matter of fact, one can and should experiment with different architectures that model the longitudinal data correctly. What is interesting, in my opinion, here is the loss function. And we have a threefold loss function that is necessary to capture the unique characteristics of these early warning systems. L1 is the negative log likelihood of the joint distribution of the first hitting time and events. And for instance, if I have a subject, a patient, for instance, who is not censored, it captures both the event that occurs and the time at which the event occurs. And if a subject is censored, it captures the time at which the subject is censored. Then I have a second loss, which is the ranking loss. And this is going to compare the order of the different events. So it will incorporate the estimated CIF calculated at different times in order to fine-tune the network to each cause-specific estimated CIF. So for this, we are going to utilize a ranking loss that is going to penalize incorrect ordering of events. So if one event happened before another, and this is wrong, and encouraging correct ordering of events. Finally, we have a more conventional loss, more similar to prediction, which is step-ahead prediction, but it serves a different role here. Longitudinal measurements on time-varying covariates, such as, for instance, the trajectory of biomarkers in the hospital, is going to be highly associated with the occurrence of different events of interest. So we are going to introduce an auxiliary task in the shared subnetworks, which make this prediction on the step-ahead covariates of interest to regularize the shared subnetwork, such that the hidden representation is going to preserve information for this step-ahead prediction. Now, this is not just a toy problem. We took dynamic deep hit to a real-world problem. So together with our collaborator, Professor Vincent Gnanaprasangam, which is the professor of urology at Cambridge and a pioneer in prostate cancer prevention and treatment, we have developed, using dynamic deep hit, a different way to survey patients with prostate cancer. Prostate cancer is a very heterogeneous disease. Some men have prostate cancer and can live long and healthy lives without any intervention, while others deteriorate fast and one needs to intervene. Currently, patients are surveyed and monitored in a one-size-fits-all fashion. And what we did using dynamic deep hit is, on the basis of this time-to-event analysis that integrates longitudinal measurements about patients over time, we can decide what's a probability of different events of interest happening, and on the basis of this, determine active surveillance that's personalized to every patient. If you want to hear how we did that and the complexities of bringing this to reality, we are currently actually testing this system in the Cambridge hospital together with Vincent. You can take a look at a YouTube video. We have actually an engagement session for clinicians that we called Revolutionizing Healthcare. And we have revolutionary clinicians from 5 different continents who are engaged with us every month. And we put the videos online. And in October 2021, we have a video about this particular application of dynamic DPA. Now, this is just scratching the top of the iceberg, because there are many more problems with early warning that are interesting and impactful challenges to address for us. I mentioned about informative sampling. It's really important to deal with this informativeness of sampling when doing time to event analysis. Another thing is that monitoring in many settings may be costly, and we need to take the cost into consideration. Also, we want to empower the humans, both the users of a system and the people who are taking the actions, to understand these early warning system predictions made by machine learning models. So we need interpretability. While a lot exists about machine learning interpretability in the static setting, much less exists in the time series setting. Also, we want to do trustworthy time to event analysis. We need to know what we know and what we do not know. And again, uncertainty estimation for time series data is limited, and for uncertainty estimation for time to event longitudinal data, even less exists. Also, different applications, whether it's finance, smart cities, or medicine, have different needs, and they may require different performance metrics to know that we have succeeded. These are just a few of the many interesting problems associated with early warning, and I really believe that much more powerful machine learning models are needed to engage with longitudinal data to provide early warning. Now, let me move to another problem, that of early diagnosis. And at the first glance, they may seem similar. So you may think, well, early warning and early diagnosis, is there really a difference? But this stage of the story, early diagnosis, emphasizing detecting existing problems at the earliest possible time. Like the prelude provided by early warning, early diagnosis focuses on timely intervention, but this time it shifts the spotlight to identifying an issue that has already emerged, but remains hidden or subtle. I will talk about healthcare, but note again that these problems are ubiquitous. They are, for instance, early diagnosis in finance is an important problem for detection of fraudulent activities, insider trading, credit card fraud, market manipulation. In climate, clearly, this is a very important problem. We would like to have early diagnosis, which may involve identifying subtle environmental changes that could lead to significant long-term impacts and catastrophe. And in engineering, for instance, and especially in transportation system, we may need to do early diagnosis that can be key in identifying efficiency and safety of, for instance, infrastructure. Let me go back to diagnosis, and I'm going to say that this is an unbelievably important problem in medicine. And what you see here is a graphic from Cancer Research UK, where you see that if patients are diagnosed early with cancer, no matter the cancer, the probability of them surviving 5 years changes significantly. This not only impacts the lives of patients, but also the financial impact associated with treating such patients with cancer. So, for instance, this is a quote from the World Health Organization, which says that the treatment of cancer is significantly less expensive if we are treating patients that are diagnosed early. To understand why this is a very hard problem, I'm going to take the following example. And again, this is in medicine, but this is generally the case. What you see here is real data from the Cancer Registry of the UK, where you see women with stage 2 ovarian cancer. And what you see in orange is the time at which surgery has been done. And diagnosis preceded it, but by just very little bit. And what we would like ideally is to move the time of the diagnosis to stage 1 cancer if we can. And similar stories happen at other stages of cancer. I just took here one of them. And what I'd like you to see is that you have some dots prior to this purple line. And these are encounters of patients. So every, on the vertical line, you have different types of patients. So the rows are different patients. And what you see in different colors is different encounters with the healthcare system. So these patients may go to some of them may go, some of them may not go to the clinician and potentially different clinicians. So these are encounters with the healthcare system. So these are sparse and also diverse observations. So unlike in the previous case, we are not monitoring somebody in a hospital, or we are not monitoring the railway or the financial system. In this case, we make just very few observations, sparse and also very diverse in nature. Let me go one step further. And again, this applies to medicine, but it's more generally the case. If the patient is healthy, then it's no problem. But then as the patient starts to have premalignant conditions, it starts to have early signs and indicators. As pathology becomes present, non-specific symptoms occur. And as it progresses and it goes to higher stage cancer disease, specific symptoms occur. So this is a tricky problem because we have very few indicators prior to severe disease. So the question is, can machine learning help in this case? How can we model early diagnosis from such sparse indicators? And I'm going to use the word indicators to mean signs, symptoms, diagnosis of different types of precursor diseases and events, which in this case may mean the final diagnosis. And they modulate the likelihood of future indicators as the system, in this case, the human body, but again, this could be something else. It could be a city, as the system evolves. So the question is, can we learn temporal relationships between such sparse indicators? Every gray ball there represents a possible indicator, and it starts to turn from gray to a color as that event is recognized and identified, as that indicator is identified. So for instance, initially we have a very vague sign, then we may have a non-specific symptom, all the way to the patient having, non-specific, all the way to having a specific symptom. And hopefully this is an early diagnosis. So what is important is to understand the timing and the interactions of such indicators in order to be able to do early diagnosis. So what indicator is likely to occur, in what order, when? This can all be discriminative because initially when we have just a very few observations, they may be very vague. And we may not know whether this vague sign, for instance, it is due to cancer or due to just the person, for instance, having a bad day. So we need to really unravel these interactions over time and to understand which event to watch for and when. To build for this, on this, we try to build a system called deep diffusion processes. And the key idea here was to systematically capture the relationships among indicators over time to do early diagnosis. How? By building such dynamic indicator networks that capture order as well as timings of indicators. So what we would like to do is learn a dynamical network G of T, T indicating the fact that it is evolving over time, which consists of vertices V annotated with binary labels saying whether an indicator occurred or not, and a set of edges, ET, which modulates the strength between indicators. So for instance, if a particular indicator VI occurs, how does this modulate the chance of occurrence of another indicator, VI? And WT is the weight associated with every edge, representing the strength of this modulation effect between indicators. Some indicators may not have among each other any modulation, and hence the weight will be zero. But how can we learn such a dynamic indicator network from data? Because what we do have available is not that. What we do have availability is individual trajectories of sequences and indicators happening over time. So what we are doing in order to learn that at the core of this is an intensity function that I'm showing in here, lambda v, which is the probability of event v occurring in a certain time window t plus delta t, given a history ht. The first term here captures the occurrence of events due to static exogenous risk factors. For instance, if the patient has smoked a lot, that may raise their baseline risk of lung cancer. The second term models the impact from past events, and each historical event adds an impulse, G of V, to the intensity function of the event V, depending on the event VI, the timing TI, and most importantly, the history HTI. Now, let me introduce just very briefly the parametric form for this. We have the instantaneous impact between VI and V, the time influence kernel that captures the decay or the increase among previous events influence, and the dynamic influence factor that depends on the full history of indicators. And this is learned using a neural network. Now, this is one particular way on the basis of which we can learn how these dynamical systems evolve over time for early diagnosis. Let us see how this is working in action. So initially, I may have just an exogenous factor. For instance, this patient may have family history or they may have smoked. And what I'm interested in is early diagnosis, for instance, for lung cancer. So this is the first indicator. And what you see is that the probability shown on the right side in blue, given this baseline exogenous factor, is evolving. Then, if I now diagnosed this particular first indicator, I'm going to change the probability of other related indicators happening, signs, non-specific symptoms, diagnosis. So what you see again, you see in green now, the probability of this second event changing as a result of the blue indicator occurring. Finally, I can continue and do that, and all the past indicators, in this case, blue and green, are telling me something. So the entire history is telling me something about the probability of the event in red occurring and how this changes with time. So this is just one way we can think of about modeling early diagnosis from such sparse and diverse information. But I really hope that the community tries to really engage with it and come up with even better ideas. Again, this is this issue of irregular and informative sampling, of screening. How do we screen these people with different types of modalities? When? Again, there is the issue of competing risks, because every situation may have multiple risks that may be of interest, and their cost may be very different. Finally, in the case of medicine, it's one patient at a time. But if we talk about early diagnosis in a financial system, which is something that I studied around a decade ago, what's interesting in financial system is that if a bank is starting to be early diagnosed of defaulting, this will have an impact on a lot of other banks with which this bank is making transactions. So there is a network effect here as well. So different applications may require us to engage with different types of issues. Let me now talk about a different and even more exciting area. Understanding why these events are happening. So understanding causality over time, which is like uncovering the plot of the story. Because it's not enough to just know that something is happening. We would like to know why it's happening and possibly intervene such that this does not happen. So this builds a deeper understanding of the dynamical system, of the complex evolving system, whether it's human body or a city, aiding both early warning and early diagnosis by revealing the essential dynamics at play. Now, I believe that causality has the potential to truly transform the way we solve a large number of real-world problems. But so far, its potential remains somewhat unlocked, since most work so far requires very strong assumptions, which unfortunately not always hold in practice in these real-world problems. So to address this, we have developed last year a new and pragmatic way of thinking about causality, which we call causal deep learning, which enables reality-centric pragmatic solutions to use causality ideas to make real-world impact by allowing flexibility on assumptions, various parametrical forms. It works with both plausible as well as partial causal structure, not only complete causal structures, and of course, we use time. Here is our work and our paper by my students, Jeroen, Christophe, and Zhaoji, and you can take a look at it. But let me say just a few words about it. So much of the current work in the research community on causality focuses on structure. However, as we know from the ladder of Judea-Pearl, we also need structural equations. And you see that on the counterfactual run. So what we wanted to do in causal deep learning, we wanted to advocate to differentiate explicitly causal models not only based on their causal structure, but also the types of structural equations. We also advocate to give much more attention to time and how systems evolve over time, and differentiate between static and dynamic methods. And the reason we call this in our paper a topographical map is because it contains this third dimension, time. So it's not the altitude, but it's rather time that creates this new dimension. Let me go in a little bit more detail why we wanted to do this type of refinement of causality and why did we construct this map to make it more pragmatic and more useful to practitioners. First, the structures are characterized in our map using an axis called structures. And in a pragmatic approach to causality, we do not have only complete causal structure and unknown, but also we introduce this rank, we call it rank 1.5, which contains plausible causal structures or partial causal structures. So we may know only just some relationships between variables, or we may just know independence between some variables, or we just know maybe due to prior knowledge part of the causal graph. So it's not an all or nothing game. Another thing that we find very important is structural equations. So the latter does not allow us to differentiate between at the extreme non-parametric models and highly parametric models. What you see here indicated by 51, 52, 53 are references in our paper, which are all very different in nature, and yet if it is to use just the ladder, they are all condensed together. And in a pragmatic solution to causality, we feel that they need to be differentiated among each other. In this way, for instance, as you can see on the x-axis of our causal map, we can differentiate between methods such as logistic regression on one hand and transformers on the other hand. Finally, we need to explicitly account for the temporal dimension, and this will allow for situations which capture exposure time, temporal structures, dynamical evolution, and I believe that this time has a very special position in causality, and current machine learning solutions which focus on causality but discard the temporal aspects are limiting in terms of solving real-world problems. So I really feel that causality is in essence a temporal phenomena, and time is something very important for us to consider. So in the map of causal deep learning, we have these structures, which are graphical models, learned or given. We have, on the other hand, and this allows solutions which practitioners to involve with different types of solutions, which depend on the type of assumptions they want to make. We have this parametric axis. And again, very importantly, we have time. And if you look in our causal deep learning map, we did that also to see where do we have methods, where practitioners can find methods and where they cannot. And it is especially with respect to time that very, very few methods are available. So let me talk a little bit about that and excite you about this topic, which I feel is underrepresented in our community. In our lab, one of the few things that we did on causality was involved with individualized treatment effects or conditional average treatment effects or KDD and IT. And I'd like to acknowledge here long-term support from ONR in this particular area. The goal, the reason we were so excited about this topic and we have studied it now for a few years is because it now enables us to choose targeted, individualized actions and interventions over time by adapting dynamically to the evolving circumstances. Let us see how this fits within this CDL map. So what we have is that IT and KDD are assuming that the outcomes, the potential outcomes, are independent of the treatment, the action, given the features. And this is a structural assumption. So this is how this fits within this framework. And again, we may have non-parametric or parametric machine learning models. And since we are focusing a lot in machine learning, I'm mainly going to talk about parametric, non-parametric models. Again, why this is exciting is because we can solve problems such as how to treat, when to give treatment, when to stop treatment. And again, this is not treatment in medicine only. It could be how to treat, for instance, a particular financial system. So not only medicine, but also, for instance, personalized investment strategies where the individual actions and interventions could mean creating customized investment portfolios for clients. And these individualized approaches could ensure that each client's financial portfolio aligns with their unique needs and preferences as they evolve over time. Another example that I was quite a lot involved in smart cities was thinking about adaptive energy consumption, where we are tailoring energy supplies to individual households or buildings based on their specific consumption patterns and needs. And in this way, we can optimize energy usage and contribute to a more sustainable urban environment, dynamic traffic management, and many others. Now, why is this problem challenging? Is because we have observational data, which in this case is this time-dependent features. We have actions or treatments taken over time, and we have static information. This forms the history of an individual. For instance, in medicine, the history of a patient. On the basis of such histories, we are trying to estimate how in the future to intervene for other patients, to learn from the basis of this data and learn how to intervene in the future. An important challenge is that in this data, we have only factual outcomes. We do not have the counterfactuals. We do not know what would have happened to these people if they were treated differently. Another important complication is the fact that this is not prediction. This is causality. And hence, we need to deal with time-dependent confounders, which are going to bias the treatment assignment. So these treatments and these actions are not taken at random. They are taken with information. And this is information that is biasing the observational data set, and we need to consider. For instance, in the case of medicine, these time-dependent confounders could be patient covariates, which are affected by past treatment, which then in turn influence future treatments and outcomes. So what you see here, it is a quite complex causal graph, which is time-dependent. So we already know that causality is challenging in the static setting, but it's even more so. There are additional challenges when we want to deal with the time series setting. Yet important challenges that we need to solve. A first attempt to solve this problem dates back to more than 20 years in brilliant work by Robbins, Hernan, and Brumbach, who built marginal structural models which look at time series data and deal with this time-dependent confounding by doing inverse probability of treatment weighting. A few years back, we were very inspired by this work, and we wanted to adopt flexible deep learning models, recurrent models, to make these marginal structural models more flexible. And this is why we created these recurrent marginal structural networks. But what we discovered very fast is that unless we have a lot of data, these type of approaches are numerically unstable and lead to high variance. So this is why we, again, capitalize on the power of machine learning to build representations in the form of counterfactual recurrent networks, which enable us to deal with this time-dependent confounding in a different way. So CRNs are able to use a novel sequence-to-sequence model that leverages increasingly available information, observational data to estimate the treatment effects over time. And the way in which we are currently, in this particular architecture, deal with bias from time-varying confounders is not by propensity scoring, but rather by using domain adversarial training to build balancing representations of the patient histories. And then at each step, CRN will construct a treatment invariant representation which will remove the association between the patient history and the treatment assignment, thereby being able to do reliable counterfactual prediction. And indeed, you see here CRN at work, and you see that actually here lower is better, and you see that CRN indeed outperforms that. But again, this is just a very small step in a long agenda. And one thing especially that I've been puzzled for a long time was the fact that these measurements in time series setting for treatment effects are not missing at random, but rather they are informatively sampled. Patients who are treated or not treated but have a particular disease are not going to be measured and sampled, and observations are not at random. So what we more recently started to look at, and this is very recent work from us, is we started to formalize this informative sampling problem as a covariate shift problem. And we showed that actually, if we don't account for it correctly, this can prohibit accurate estimation of the treatment outcomes. So what is interesting here is that we do not only learn from the value of the observations, but also the timing of the observations. And again, I feel that this is just scratching the surface in this particular problem. Many interesting and impactful problems in causality over time. Here we are really at the beginning, and we really need to exploit partial knowledge, partial structures, structural equations, and time to make advance with causality in the real world. And I really feel that by being pragmatic about this, we can bring this type of ideas and solutions to solve real-world problems. And if you are a researcher, I'd like to invite you to take a look at our map, because our map contains many empty spaces where there are not methods, or there are very few methods available. So please take a look and see which areas are uncovered, and quite a lot of them are, and engage with it and develop solutions. Finally, I'd like to say something about what I believe to be the ultimate frontier, which is achieving a comprehensive understanding of complex dynamical systems themselves using data and machine learning. And the reason I think that this is the ultimate frontier is because this encompasses everything learned from the preceding stages and goes further, because it tries to understand how systems characteristics look like, how they evolve, how they respond to interventions, how they exhibit emergent behaviors. So the ability to discover, analyze, and understand dynamical systems on the basis of the available data using machine learning can have far-reaching applications in all the domains I mentioned before. So what I'd like to do is, I'd like to, if you like, create a new frontier which goes beyond even causality, which is learning, discovering, analyzing, and impacting dynamical systems from data using machine learning. Let me take just a subset of this problem and explain why even this subset is hard. What I have is observations about a dynamical system. Again, can be a patient, or for instance, maybe pollution measurements about the pollution level of a city or a financial system. So this is my data set, a set of observations over time. And what I'd like to do from it, I'd like to learn using machine learning. I'd like to learn the dynamical system that has generated this data. So I'd like to discover a system of transparent ordinary differential equations that characterize this system. Even the simplest problem is hard because the time derivative is not observed. So wonderful tools such as conventional symbolic regressions are not applicable. Also, it is difficult to estimate the time derivative because the states are observed only sporadically and with noise. And at times we may have even very few observations. And again, two-step symbolic regression is often failing. And finally, even non-transparent methods, such as wonderful neural ODEs, have challenges because the true initial condition is unknown and is difficult to infer from data and is sensitive to these initial conditions and also computationally challenging. So we made a little advance in this area, and I'm actually very proud of the advance that Zhao and Christophe, my two students, have come up with, which is discovering such closed form ordinary differential equation from observational data, which represents a first step in learning and discovering dynamical systems from data. Let me tell you a little bit on how we were able to do that. To understand this, I'm just going to say that we need to familiarize ourselves just very briefly with this variational formulation of ODEs which we use, because it enables us to characterize ODEs without referring to derivatives. And this is achieved in this variational formulation by introducing a special functional that takes the function f, the trajectory x, and something we design. That's the reason I want to show this to you, because here we need to play the engineering hat. We need to design testing functions g. This is something we can design. And then the value of the functional is the sum of these two integrals. And it is important again to note that this does not involve the derivative of x, but rather the derivative of g. And as I mentioned, g we can design. This functional then should be zero for all the testing function g that are continuously differentiable and vanishing at endpoints. And this enables us, this theory enables us, the machine learners, to build powerful machine learning methods that use this to design loss functions, because we can minimize the value of this functional, which corresponds to finding better approximations for the true ODE. We prove this formally in the paper, but that's not the point. The point is that we can indeed, using these insights, build loss functions correctly to learn ODEs. Our algorithm decode consists of two-step, preprocessing and optimization. In the preprocessing step, we take the data set of observed trajectory and denoise them and interpolate them to get estimated trajectories. And then in the and note here that we estimate trajectories rather than derivatives. And this consists of the functional defined earlier. And what is nice is that we were able to construct testing functions, which actually are very popular in signal processing, another field of engineering, which are sign functions. And then what is good about this is now symbolic regression can be used. Let's see if this decode type methodology works. And for that, first, let's look at some traces and see if we can learn something we already know. So the reason we are going to do that is to see, can we really learn from data things we already know to verify the power of these methods? And we focus especially in our work on dynamical systems that have asymmetric growth with saturation because they are all over the place, in finance, in medicine, in physics. And we wanted to compare to the only solutions existing, which are a variety of two-step symbolic regression. And what you can see is that for all the real-world settings, settings with noise, settings where we are irregularly sampling, we have few samples. Decode indeed significantly outperforms the other methods in terms of discovering the dynamical system. And also, interestingly, if we have chaotic systems, non-periodic systems, we are also doing a lot better than even non-transparent solutions like neural ODEs, because such solutions struggle with the fact that we cannot even estimate the initial condition, while Decode can. Let's take this then to something real. Can we discover something we do not know? And for that, we looked at temporal effects of chemotherapy on tumor volume, and we tried to learn this dynamical system from clinical trials on cancer patients. And what we were hoping to learn is, can we really learn these trends? Can we learn that initially, when chemotherapy is given, the tumor, which is indicated here, the tumor size, which is indicated here with the y-axis, is initially over time, which is indicated on the x-axis, initially goes down, and then we have a relapse. And what you can see is that indeed Decode is able to capture this trend, unlike symbolic regression. Now, is this a true discovery? Can we really take this? Is this real? For that, we need to engage with practitioners and take this to real data and real experiments. So still a long road to go, but a very exciting one. And I really still believe that this dynamical system discovery, analysis, and also interventions on such dynamical system represent the ultimate frontier. Why I'm so excited about what machine learning can do to study, understand, and guide dynamical systems is because they are all-encompassing. They are really fundamental. If we can model and understand well dynamical systems, and we have a transparent way to do so, then I believe that many fields that we are engaging with today, from reinforcement learning to time-to-event analysis, survival analysis, to causal effect inference, to graph learning, all of them are going to be transformed if we are able to really conquer this problem. Today, I took you on a journey of 4 canonical problems that I think are very important to solve to really impact a variety of application domains. There are many more. I just highlighted 4 that I find especially important, and I feel we as a community can do a lot. And if you are interested to discuss not only with me, but also with my students, we have an engagement session dedicated to challenges such as this that we call Inspiration Exchange. If you are interested, we have these sessions online every month, so you can take a look at our website and join us. And finally, I would like to reiterate that I strongly believe that a fundamentally new paradigm is needed for AI and machine learning, which is really this reality-centric AI agenda, which is focused on reorienting AI and ML towards the complexities of the real world. So please join us in solving important and non-trivial problems for humanity. Thank you very much.